What I have here is the bridge rectifier. So these are my diodes 1, 2, 3 and 4. Out of the 4 ends, one end is connected to ground. At the two opposite ends I have the output from my transformer, which is approximately 40 volts peak to peak, as we saw in the last video. And the last end is my output end, which I'll connect to the capacitor plus further circuitry, right? So this is my bridge rectifier. First thing that we'll do is look at the rectified output, right? So let's see the oscilloscope output. Okay, this is my rectified output here. Okay. And if I measure it, so this is what I get. I get something like now here. Okay, let's look for the peak to peak value because it's only single cycle or only positive cycle. So it's about 18 volts. So that's what I expect from my rectified transformer output, right? Now this is still an AC signal because or let's call it time varying signal because of the rectifier action only. So what we'll do is we'll put a 470 microfarad capacitor between this output and ground, and that would help us in filtering out the AC part. And you see, as soon as I put the capacitor in, the output changes considerably. It looks much more like a DC flatline now, and if we look at the mean value, it's about 17.2 volts, right? What we can do is we can also measure the ripple after the filtering, and for that what I'll do is I'll put the channel 1 in AC coupling mode now to see the ripple, and now I can go and increase the scale. So if I increase the scale to up to few tens or hundreds millivolts, then I can see this ripple which is there riding on the DC. Now there is no DC part, so the output DC is constant at 17 volts. This is the fluctuation over that DC, and we can measure its amplitude. It's of the order of 60 or 70 millivolts, right? So using this information we can find out the ripple factor for our rectifier. Now the important thing to note down is this ripple factor is because I don't have any load, any external load connected to the system. I am seeing the output right across the capacitor, right? So if we start connecting external loads, then we can see its effect on the ripple, right? So for example, what I'll do is first I'll connect a heavy load or high impedance load. So let's take a 1 kilo ohm resistance and connect it across the output, that means parallel to the capacitor. And now if I measure my ripple, we can see that suddenly the ripple value has gone up by a substantial amount. On readjusting the scale, I can now measure it. It comes out to be about 500 or 550 millivolts, right? And if we see the DC of this output, again putting channel 1 into DC coupling, right? Readjusting the scales, we can see that now we can already see some fluctuations on that DC, which was earlier quite flat. And if we measure the DC, we can see that the mean value has come down to about 16 volts from 17.2 volts. So that's the loading effect of the resistor, as well as because the RC constant, now there will be some amount of some higher degree of ripple there. What we can do is we can remove this high impedance. We can connect a relatively low impedance, for example about, let's say about 100 ohms, right? So that the RC changes further. And now if I try to measure the ripple, you can see now in the DC itself I can see a nice ripple, and the DC value comes down to about 11.7 volts, right? And if I quickly change the channel to AC, we can measure the strength of this ripple now, which will give us the actual ripple factor in this case, and that's of the order of 3.12 volts, right? So now it's about 25% of the actual DC value.